Okay, now I'm going to get my screen share started. Let me see if, no, PowerPoint's not open yet. Let me get this started. I had all this done before, but I had to close it down in order to shut my computer down. Now, this may have been what knocked it out. I don't know. Hopefully not. But I can't get Chapter 5 PowerPoint to open. I don't know what the problem is. It opened quite nicely. Here it comes. Okay. Chapter 5's open. And we're opening Chapter 8. All right, Chapter 8's open. So let's go back to Zoom. And I'm going to share screen and bring in Chapter 5. Okay. Now, let's go from current slide. All right. Finally, we're back in the saddle again here. First, any issues, concerns, problems, situations, anything from y'all? Everything okay?
Yes.
All right, good deal.
I had a question
okay.
on the homework.
Okay.
So for number 1, on page 134.
Okay, got it.
I had got the answer. It was 380.
Okay.
And then I also got the number 38.4.
Okay, so you got two answers.
I wasn't sure which was right.
Okay. So you're leaving it as multiple choice for me, huh? No, I'm just kidding. Okay. Okay, let's see. You're talking about Chapter 5. This is page 134, you said. Okay. Now, why or how did you get two different answers?
Well, the book said 380.
Yes, yeah, that's what...
But the calculator said 38.4.
Ah, okay. Okay, it may be a round-off error then. Okay, well, no, it's more than that. Okay, now, if the answers in the back are anything like the answers on the test bank, they could easily be wrong. Okay, so let's work through the problem as we have it. Now, in some of my other classes, I've had several requests to use the whiteboard, unless you tell me if this is better, worse, or, what I have been doing is holding up a piece of paper with the worked out solution. Here's the whiteboard. Tell me which you like better, worse, indifferent, whatever. The problem with the whiteboard is that I have to write with my finger on the keypad. It's terrible, okay? But it does do. If it's text, I can type it using text, but basically something like this. So here we have a cart on wheels, weighs 2,400 Newton. So I'm not going to draw a very good cart, but here's what my cart will look like. This is the cart, ugly cart, on wheels. Here's the ugly wheels. Okay? And here's the ground. There's the ground. That's supposed to be level. Just pretend. Okay. That weighs 2,400 newtons. So that's the force downward. In the book, we've been calling that F sub W for the force due to weight. Okay? and this is 2,400 newtons. The writing is terrible. Don't be laughing so loud. You turned your microphones off so I can't hear you. But cut it out, okay? 2,400 newtons. Okay, that is the weight of the cart. Now, that is also the force that the supposedly level surface here is pushing up on the cart. And that's often called the normal force. And because the cart's not falling through the pavement, nor is it flying up in the air, the normal force must also equal the weight, because there's no net force vertically. So this is the normal force. And that must also be 2,400 newtons. Now you might say, why don't we just use weight? Well, the formula doesn't use weight, it uses normal force. Okay. And by the way, the basic equation is at the top of the page. Okay, it also tells us the coefficient of rolling friction between the wheels and the floor. That's supposed to be a floor, not in my house, okay? The coefficient of friction, mu, and this is of rolling friction. I'm going to put a little r down here, though the book doesn't do it. Coefficient of rolling friction is given to be 0.16. Okay, that's supposed to be a 6. What force is needed to keep the cart rolling uniformly? So in other words, you're going to have to supply a force in this direction to keep it rolling at a constant rate, which means you've got to exactly counterbalance the force due to friction, which is always opposing the motion. So this is the frictional force, and if my memory is right, that's F sub F is what the book uses. It's right here on this page. Let me see. Yeah, F sub F. Well, what is F sub F? F sub F is mu, that's supposed to be a mu, times the normal force, F sub n. Okay? Now, I'm going to pull out my handy-dandy calculator and see if I get the same thing you did. Okay? I just had a message. I didn't notice what it said. Okay. Here's the calculator. And according to this, the force due to friction here, which is exactly the same as the force you're going to have to be exerting on it, because if you're going at a constant velocity, the net force is 0. Only when you accelerate do you have a net force. So let's see what that frictional force is, which has to be your net force pulling in the opposite direction. So that will be 0.16 times 2,400. And what answer did you say you got? Okay. I think I see what part of the problem may be, but it probably isn't the whole problem. Okay. Now here's what my calculator showed. Okay. 384. But that's 3 digits, right? Remember, here, we only have 2 digits here. We only have 2 digits there. We only have 2 significant digits. So they take this force, and I'll write it down here, the applied force, which has to equal the frictional force, so I'll call it force sub A. The applied force to keep it rolling is, you write down the first 2 digits, 3, 8. Okay? Pretty ugly writing, I admit. Really ugly. But look to the right. You count off 2 digits. Look to the right. It's a 4. 4 is less than 5, so you drop the 4 and just put a 0 down. And that's where they get 380 newtons. So the back of the book is correct on it. If you had answered 384, I would just round it to the correct number of significant digits. That would have been an okay answer. The most correct answer is 380 newtons, because that has 2 significant digits from here. You see, if either one of these zeros would have been significant, they would have put a bar over it. They didn't. But whether they did or not, there's only 2 significant digits here. You only have 2 digits. That 0 is not significant. That's just a placeholder telling you there's a decimal after it. So you can only have 2 significant digits of answer. You cannot give me an answer of 384 newtons because you only have 2 digits of precision. Okay? 3, 8, and then you put a 0 after it. Does that answer your question? Anybody?
Yes, sir.
Okay. So you're okay with that?
Should it be 38.0?
No. The answer here is 384. Okay? You don't have
Yes,
enough.
sir.
You don't have enough digits to support 384. You only have enough to support 2. So you have to put a 0, just like they have these 2 zeros here. They're not significant, but you don't throw them away and make it 24. It's 2,400. This is 380. The 4 rounds down to make it 380 newtons. If you made it 38 newtons, that's a tenth of what this is. You can't just throw away the 0 or the 4. You put a 0 in place of the 4. Does that make sense?
Yes, sir.
Okay. If that would have been a 385, then we would have made this 390 newtons. The next closest 2 significant digit to that answer. So it's either going to be 380 or 390. Since it's 384, that rounds down to 380. Does that make sense? Yay or nay?
Yes.
You okay?
Yes, sir.
All right, good deal. Good question. Excellent question, by the way. Are there any others?
I also had one on number 7.
Same problem set? Same page?
Yes, sir. On
Okay.
the same page.
Okay. You're going to make me draw something else, aren't you? Okay, I got you. I'll remember this. Okay. Number 7. A tow truck can deliver 2,500 pounds of pulling force. I wish that I had left my cart there. I would have pretended that's a tow truck. But let me see if I can draw a tow truck. Y'all are going to laugh again. Okay, I can hear it coming. Okay, here's the tow truck.
You don't have to draw it out.
Okay, thank you. All right, so he's going to deliver a pulling force of 2,500. So let's call this the applied force. That's what I called it before. The applied force, the pulling force, and that's going to be 2,500 pounds. This time we're in U.S. customary system. 2,500 pounds. They like those numbers, don't they? Okay. When you have units, please list them. Okay. Tow truck can deliver 2,500 pounds of pulling force. What is the maximum weight truck that can be pulled by the tow truck? So we got this tow truck pulling another big old truck that broke down by the tow truck if the coefficient of rolling friction of the truck is 0.10. So this big old truck over here, and I'm just going to do a big blob here. That's going to be what you're pulling. Pretend it's got wheels on it, okay? The coefficient of, well, here's the frictional force here, okay? Now that frictional force, that's F sub little f, always opposes the motion. We know that's going to be equal to mu. I'm not going to put a subscript there. That's the coefficient of rolling friction. Here, in this case, it's 0.10. Now, I'll get to that in just a second. Times the normal force. Okay. Now, pretend we got wheels and everything else and make that look like a truck. The normal force is the force the road is pushing upward on that truck. That's equal to the weight of the truck. Okay? Because the truck's not flying off the road, nor is it crashing through the road. So these two forces have to be equal. This is the normal force, and that has to be equal to the weight. So here's the normal force. Here is the weight, F sub W. That's the force due to weight, pulling downward. Okay? So since these two have to be equal, this is what you're looking for. What is the maximum weight truck that can be pulled by the tow truck? So the frictional force will be 0.10. Now I'm going to write it the way the book did. 0. Point. Is someone else trying to get in? 10. Now that's a dimensionless quantity. Okay? Now, I usually slash my zeros. I haven't been doing that because it's hard to do. But this 0 is just a placeholder, showing you there's a decimal right there. This 0, however, is significant. It's got to be. Any zeros following a decimal sign, after a number, after a decimal sign, those are significant. Otherwise, you just said 0.1. 0.10 means you got it to 2 significant digits. Okay? This is only 2 significant digits. So we're going to come up with the weight of the truck, which is equal to the normal force, and that's this. Well, this frictional force has to equal the weight of the truck. Not the weight. The pulling force of the truck, the applied force of the truck. That has to equal exactly this one. So all you're doing is pulling this mass back here. You're not necessarily accelerating. You're just moving it. No acceleration, so the net force is 0. Between here and here is 0. These are equal. I didn't quite draw them equal, but just pretend that I did. Okay? That looks a little better. Same thing here. These don't look like they're equal, but just pretend that they are. Okay? So this force will equal your applied force. That's 2,500. So this has to equal, I'm not going to put all the things, 10. I will put this 0 because it's a significant 0, times the normal force. Well, the normal force is also the weight of the truck, and that's what we're looking for right here. So in order to solve that equation, divide both sides by 0.10. Divide that side by that, divide this side by 0.10. You don't have to put the 0 in there, but I'm doing it for effect here. So you should be able to do this in your head, but I'll show it on the calculator. Okay? Okay. So it's 2,500, 2,500, divided by 0.1. You don't have to put the other 0 there. And when you do that, you wind up with 25,000 pounds. This truck could weigh 25,000 pounds, and this tow truck still be able to pull it, even though it only weighs 2,500 pounds. Why? Because the weight of this truck is being supported by the road. This isn't lifting the truck, it's pulling the truck. The coefficient due to the friction is 0.10, so that answer here is 25,000. And the 2 and the 5 are significant digits. Those last 3 zeros are not, but you still write them down. I mean, that's part of the answer. Okay? So your answer here is this weight, which is the same as the normal force, has to be 25,000 pounds. And this is painful to write and probably more painful to watch. I'm not going to slash these zeros. I can barely get them written. Okay, and that answer is in pounds though. Okay, how'd the back of the book do? Did you look?
They did the same thing.
They did. Well, lucky them, huh? Okay.
Yes, sir.
All right. Do you see why it's true?
Yes, sir. Now I get it.
All right. Good deal. Any other questions? Excellent questions so far. And both of those 2 and the 5 are significant. The 3 zeros are not. But you don't throw them away. It's not 25 pounds. That would be not a very reasonable answer. It'd be 25,000 pounds. Okay? Now, here's what I was saying, why it's pretty easy. You could have done this in your head. Move this decimal one place this way, and that makes it a 1. Move this decimal one place this way. We have to put an extra 0 there, and 25,000 divided by 1 is 25,000. So you didn't need a calculator for that, but I wanted to show you the calculator got it right. All right, good deal. Any other questions? Okay. If not, now my memory and my mark was that we're beginning 5.5 today. Is that right? Okay. So what I'm going to do is change my screen sharing to go back.
You said 5.5?
5.5 on page 136, just one page over from where we were answering those questions. And why in the world are there 2 PowerPoint shows here? I don't know. Okay. Now, I'm pretty sure we're almost at the end of the section here. I don't see... Yeah, okay. We will be starting with, in the next section, this slide. Okay? But we're not there yet. In fact, so let's go on to back to this slide. That was one we had earlier on friction. That was the one on page 132. As I said, the PowerPoints here are pathetic. All right? Now, what we're dealing with here is total force in one dimension. Were there any other questions before we got going on this? I did that, and then it didn't go to current slide. It went wherever it wanted to. So let me page down until we can find... Oh, there it was. Not many slides here. Okay. In the examples used to illustrate the law of acceleration, we discussed only forces, single forces. We need to remember that forces are vectors. Now, can you hear me okay?
Going in and out.
What's that?
You're kind of going in and out.
Okay, that's what I was just going to ask. Found out what I have to do is put the book right on the computer. So, is it still going in and out? Did someone say something? Can anyone hear me? Yes or no?
I hear you.
Okay. Mercy sounds awfully garbled. Have you been gargling? No, I'm just kidding. Okay. Either my microphone or my speaker or your microphone must be not great. Can you hear me okay, Mercy? Yes or no? Mercy, you can't hear me? You cannot hear me at all. Is it garbled? Can you hear me? Can you hear me?
Yeah, but your speaker has a problem.
What's that again?
The speaker?
Mika? Is that what you said?
Yeah, I think your microphone.
Okay, somebody's microphone is really garbled. Okay, I don't know if it's my speakers or your phone. Can other people hear me? I thought I heard Jalen okay. Can you hear me? Jalen?
Yeah, I can hear you now.
I can hear you.
Okay, Jalen's coming in very clear. Mercy, that sounded clearer then. Okay?
Yeah.
Now, what I guess I'll have to do is hold the book in my lap because it seems like when I put it on the computer, it messes things up. Okay? So I won't put it on the computer again. So what we're talking about here, multiple forces on one object, okay? As long as they're in the same direction. Now this could be this direction, that's the same direction. These two are the same well, they're in the same line, but in opposite directions, okay? These would be different, okay? This was going this way, this one. That's two-dimensional motion. We're not doing two-dimensional motion. We're only doing one-dimensional motion. Motion along a line in whichever direction it's going. Same direction, opposite direction, whichever, okay? That's what we're talking about in 5.5. And here's the blurb. Now, does everyone have a book, but some of you not? Answer. Does everybody have a book? Yay or nay? Yes, everybody does. Does anyone not have a book? Everybody has one. Good. I won't have to type these out, okay? So here's the blue box near the top of page 136. When forces act in the same or opposite directions, that's in one dimension, the total or the net force can be found by adding the forces that act in one direction, subtracting the forces that act in the opposite direction. Okay? That's the deal. Okay? And they say, and it's very true, it pays then to use vectors, because that makes it pretty clear. All right? Now I'm going to go back to my slide, my white page, if I can find it here. Okay? Back to my whiteboard, that's what they call it. Okay, I'm going to clear that one out of the way. All right. Now, here are two guys pushing on a crate. Okay? And I'm not going to draw very pretty guys. Okay? But here's the crate. It's not going to be very pretty either. In fact, it's pretty ugly. Okay? It's ugly, ugly. Okay. Here's the crate. Here's one guy pushing on the crate. He's kind of a short guy, and he's pushing on the crate. Okay? And his buddy over here is a little bit taller, and he's also pushing on the crate. Okay? Now, it's not necessarily that the taller guy is stronger, but in this case, they drew him to be that way. That's supposed to be his legs there. Okay? The taller guy is pushing with 175 pounds of force. So he's pushing in this direction with 175 pounds of force. That's a pretty ugly 5. Okay? Now, little guy over here is pushing with 150 pounds of force. Okay, 150 pounds of force. That's a pretty ugly 0. Okay, but they're both pushing in the same direction, so let's take that direction to be positive. Add the two forces together, and what do you have? That's a 175. I don't know if you can read it. 175 plus 150, 325. So the total force on the crate is, oh, that's ugly, 325 pounds of force. Now, we don't know if the crate's moving or not. We just know the total force on it is 325 pounds. Okay? Does that make sense? And this is to the right. Ooh, goodness, that's ugly. Okay? Now, the thing about vectors, they have direction. So you can't answer a vector question unless you also include the direction. So since little guy and big guy are both pushing to the left, to the right. Whoops, here's somebody else coming in. Can't see who it is. It's iPhone something another. Who's the new iPhone that just came into class? Can anyone tell? We're up to 6 participants. It's all it says is iPhone. Okay. Can someone tell me who iPhone is? I can't make you mark you present unless I know. Does anyone know who is who? Whose iPhone just came in? Your microphone just came in and went off. Who was that? Help me, somebody. Does anyone know? Who?
No, I don't.
Okay. Who just came into class with an iPhone? There, nope. I know it's not Jalen or Mercy or Mika or Mary or Macy or Manessa. Who is the other person? Just came into class. The sixth person in.
He said his name is Devin Verdell.
Okay. There is his first time here. And you go by Devin? I guess so. Okay, can you, I heard a little noise. Okay.
Hello?
Yes, is this Devin?
Oh, yeah, it's Devin Verdell.
Okay, got it. All right, got you in. Welcome to the class.
I appreciate it.
Now, I won't go over everything, but let me go over this one thing with you. Okay? Now, it's going to take a couple minutes away from class, but I'm going to, you won't see my screen for a minute here. I think you'll still hear me, but I'm going to pull up my blackboard. And it takes a while to get there because it's not an easy thing to do. I hope I can get to it here. There's so many things open. Okay, here's Blackboard. Now, obviously, you know about Blackboard because you got in the class, okay? But I've lost it, okay? Where is my Blackboard? There it is. Okay, there it is. So let me log in. I want to show you some important things. Okay, Mika must have had to get out and come back in. And I just lost this again. Okay. So let me see if I can. Say again? Okay. Now. Here's Blackboard. Okay. Wait, it's not there yet. Sorry. I thought it was there, but it's not. This is all my courses. Y'all don't have this many, I hope. There we are. This one right here. So obviously you must know about it because you got in the class and you found the announcement. Well, I want to point out to you a few things. The syllabus is there, of course. I'm not going over that. Well, I didn't think I was going to go over that. Okay. To open the syllabus, you hit these three dots here, or you click on those three dots. I'm not going to do that. I've already done that, and I'll show you where I did that. My locator card is here. Same deal. The PowerPoint slides are here. They're pretty pathetic, but they're there. Here's what I want to show you. The YouTube videos. Okay? If you click on this, this is a web link. So if you click on this, you go straight to the YouTube videos. Now, the ones at the top are the ones from last term, okay?
Okay.
All right. The ones at the bottom are the ones from this term. So I'm going to go to the bottom. I'm leaving the top ones up there, and there's a reason for it, and we'll get to that in a few minutes, okay? Here are the ones at the bottom. This one right here, number 18, is called, I can't, oh, wait. Let me get this. You can't see it. I'm sorry, I forgot to bring it back up. I think it's this one. Okay, can you see my YouTube videos now? Yes or no? Yes or no?
Yes. Yes.
You can. Okay. All right. This one right here, unfortunately, I've got this thing in the way. Let me see if I can move it out of the way. You can't tell what I'm talking about because you don't see it, but it's in my way. Here's the one on the syllabus. Go listen to that video. That talks about the syllabus. It talks about my locator card. It talks about the PowerPoints. It talks about everything we do in the class. It also got started in Chapter 5. Under that is the one we did. That was on Thursday of the first week. Then on Tuesday of last week, this was the video, I think. Okay? Now, Thursday of last week, I could not do the video. Okay? And the reason for that is my memory went out on my computer. So I couldn't record. So to get that one, and this is good for everybody, and by the way, I'm recording, by the way, if you haven't gotten here. You can't see it, but over here is a little icon that says we're recording 36 minutes into the class. Okay? So go up here. This went through 5.1 to 5.3. So now you have to go to the top part. And there you see, here's from 5. Well, I had it, but I lost it. Sorry about that. There we go. There is 5.3 to 5.6. If you go to that, you get 5.3 and 5.4. We're in 5.5 now. So that's where you'll pick up the ones that I missed. Now, if you look at this, you'll see there's a screen that I've written on, and you'll see me write. Back then, I had a computer that would work that way. This computer won't. That's why I have to go to the white screen that we had and draw with my fingers, okay? This one I was actually to write with a pen, an ionizing pen. So this is where you can catch up anything you missed, okay? Now, let me end that YouTube video, and then the rest of this is the library link, and that's about it, okay? And up here, this icon here, that's the messages. Under messages, I'll click on that for right now, and Mercy sent me one and sent me an answer back, and there she sent me something else. That's the syllabus I get. Oh no, that's Mercy sent it to me. Okay, so anyway, that's where you can send me messages or I'll send you messages. And I promise you, sometime after class tonight, I'm sending you the first test. If we can get that far, which I think we will. Okay, so I'm going to get out of my Blackboard now.
Okay.
And you can follow the rest of it on Blackboard. Okay? Now,
All right, I appreciate it.
glad to. Welcome to the class. Okay. Let me go back to, I think where I last was the whiteboard, wasn't I? Okay. Can y'all see my whiteboard again? Okay. So this is a picture of the example 1 on page 136 at the beginning of 5.5. 2 guys pushing on a crate, one with 175 pounds of force, one with 150 pounds of force, pushing in the same direction. The total force on the crate is the sum of those two, 325 pounds. Now, what if, I'm going to leave this picture up here, what if the same 2 workers are pushing on the crate to the right, but the motion is being opposed by static frictional force of 300 pounds to the left? So that means the friction always opposes the motion. Okay? So here is the frictional force to the left, and that's called F sub F. Capital F for force, little f for friction force. That's a sub-force. And that frictional force is, they didn't tell us how they got it, they just said 300 pounds. Now what they do with this 300, they put a bar over that second zero. What does that mean? All three digits are significant. The first is significant because it's a 3. The last one's significant because of the bar. So that means everything in between is significant as well. You have 3 significant digits, and that's your frictional force of 300 pounds. But that 300 pounds is in the opposite direction, to the left. This one was to the right, okay? So what's the net force that the crate is feeling? 300 pounds to the left, 325 to the right. The net force here would then be, and I'm going to call it that, F sub N. Now the normal force is capital N. I'm going to put little n for net force, and that would be, hopefully you've already figured it out, 25 pounds. Okay, 25 pounds. Now I can almost hear Manasseh screaming at me saying, wait a minute, where's the third digit? Aha. Those significant digits, like we just had before, they work primarily with multiplications and divisions. In this case, you had 2 numbers with 3 significant digits. You could subtract them. Here you had 2 significant digits that you added. Now, I don't remember that they put a bar. Yes, they did. I left it off. I should have put the bar over that 0. 3 significant digits there. So this had 3 significant digits. This had 3 significant digits. This only has 2. But whenever you're subtracting, you can't add another significant digit just because you subtract it. So now we're down to 2 significant digits. If you put a 0.0 here, that means you can measure that to the nearest tenth of a pound. You're not measuring this to the nearest tenth of a pound. You're not measuring this to the nearest tenth of a pound. This is to the nearest pound. That's to the nearest pound. This is to the nearest pound. So you're dropped to 2 significant digits there. So that's why the answer is only that, but this is also to the right. And I'm just going to draw the arrow here because I don't want to write the word right. Okay, I could, but I'm not going to. Okay, does that make sense? Add the 2 forces in one direction, subtract the one in the other direction. Whatever you have left, that's your net force. Actually, what this book calls it, and it's harder to write, but I'll try to write it for you at least one time, they call it the sum of the forces. That is called the sigma, and that's the sum of all your forces. And this is a pretty ugly picture, okay? Sum of all your forces is what I call the net force. They call the sigma force. Okay. Now, same picture, same crate. Okay? They say that crate in example 2 has a mass. So now they're talking about the mass of the crate. The mass of this crate, remember mass is the amount of material that's in it. Pounds do not measure mass. Pounds measures force. Okay? So this is a force, that's a force, that's a force, that's a force. This is a force. Those are all directional. Mass is just how much material there is. It doesn't have a vector. It's not a vector. So this is a mass of 5 slugs. Okay? But they're actually giving it to us as 5.00 slugs. Slugs is a weird unit. It doesn't even have an abbreviation. Nobody but the author of this book ever uses slug. That's an exaggeration. It's 5.0 slugs. I wish it had an abbreviation. I wouldn't have to spell it out every time. Okay? So the mass of that is 5.00 slugs. What is the acceleration when the workers are pushing against the frictional force? Well, if you remember Newton's second law, that the net force is equal to the mass times the acceleration, that tells you. So The book doesn't use net force. Well, he sort of does. He just says little f. He leaves off capital F. He leaves off the little n. So that's the formula he's using, Newton's second law, that the net force, or the sum of the forces acting on that crate, is equal to, this is Newton's second law, the mass of the crate times the acceleration of the crate. Okay? Well, we know this net force is 25 pounds. I can't write this too well. 25 pounds. Now, what is a pound? Yuck, I don't want to write this. A pound is a slug foot per second squared. Let's just pretend I wrote that out. Slug feet per second squared. I'm just going to write the word or the abbreviation pound because it's much easier to do. And that's equal to the mass, which we know to be 5 slugs. Why am I writing mass then? Let me erase that. Okay. Actually, it would be better if let me do it this way. We're looking for acceleration. So let's solve this equation here for acceleration. You divide both sides of the equation by mass, and you get acceleration is equal to force divided by mass. And that would be, the force is 25 pounds, 25. Now I'm going to write pounds, but I want you to write down slug feet per second squared. I just, with this pen, I can't write all that. That's slug feet per second squared, and you're going to divide that by 5.00 slugs. 5.0. Ooh, that's ugly. 0. Now that's a decimal point in there. It's not a very clear decimal point. 5.00 slugs. I'm just going to abbreviate that as a SLU. Okay, because I don't want to write anymore. Remember what your pound is? It's a slug foot per second squared. So this slug here cancels out the slug that's in the pound and leaves you with just feet per second squared. That's a unit for acceleration. Velocity is feet per second. Distance or displacement is feet. Acceleration is feet per second squared. The rate of change of your velocity. Okay? And if you divide 25 by 5, obviously the answer you get is your acceleration is equal to, now here's where another trick comes into play. 5 will go into 25 5 times, but you have 2 significant digits here, 3 down here. You go with the fewest, which is 2. You've got a decimal here, so you put your decimal in place and just put 1 more, and this unit answer will be in feet per second squared. And that's hard for me to write. I'll try feet. That's ugly, isn't it? That looks like a capital A. It's not. That's FT per second squared. Okay, feet per second squared. Why only 2 significant digits? Because your numerator only had 2. You couldn't make up a third significant digit there from the subtraction. Subtraction usually can easily lose you significant digits. Multiplication and division don't. Subtraction does. So it's 2 digits on top, 3 on the bottom. Your answer is in 2. 5.0 feet per second squared. And that is the answer they get. Does that make sense? Any questions about it? Anybody? Okay. Do you prefer me writing on the whiteboard, or do you prefer me writing on a piece of paper and hold it in front of the camera? Whiteboard. That's what everybody else says. Thank you very much. No, I'm just kidding. Okay. So let's go on to example 4. All right to clear this one? Yay or nay?
Yes.
Okay, we're going to clear it. I'm going to try to clear it. There it goes. Example 4. 2 workers are pushing in the same direction on a large pallet. I wish I had kept my picture up there. The force exerted by one worker is 645 newtons. They're pushing in the same direction. So here's worker 1. I'm not going to build him. I'm just going to call him worker 1. And he's pushing in one direction with 645 and what was the unit? Newtons, wasn't it? Yeah, 645 newtons. That also is a unit of force, but that's in the SI system. System International, which is also we often call the metric system. Now, the force exerted by the other worker, and they said it's in the same direction, so worker 2 is also pushing on the pallet. I'm not going to draw the workers. I'm just going to call him worker 2. And he's pushing in the same direction with a force of 755 newtons. 755 newtons. I may stop slashing my 7s too because it's hard to get them right. 755 newtons in the same direction. Okay? Now the motion is opposed by a frictional force of 1175 newtons. So here we have a frictional force that's opposing these two motions, and this frictional force, that's your capital F sub little f, that means the force due to friction, and this is going to be 1175. Now, I didn't leave enough room here. 11, that's supposed to be a 7, 5 newtons. Okay, now looking at that, you have 3 significant digits here, 3 here, 4 here. But guess what? You're limited to 3. But actually when you add these two, because adding, like subtraction, you just keep to the nearest thing. Well, when you add these two together, that's a total force in this direction, an applied force in that direction of, help me out, I believe that's a 0 here, and a 0 here, and a 14 here, right? So your total force in that direction is 1400 newtons, and you oppose that with 1175 newtons. And if I can do my subtraction right, I think that's going to come up 225 newtons. Is that what you got? So the net force, okay, the net force acting on this pallet is 225 newtons to the right, same direction that the workers were pushing. Okay? Thank goodness they didn't give us the weight of the pallet and ask us to do the acceleration. We could have done that. I'm sorry, not the weight, the mass of the pallet. If they had given us the mass of the pallet, then you take that mass, this is the net force acting on it, divide the net force by the mass, you will get the acceleration. But in that case, it would be meters per second squared, because the mass in the SI units is kilogram, and a newton is a kilogram meter per second squared. So if you divide by kilograms, you get meters per second squared. All right, that finally finishes 5.5. Homework exercises here would be any of the odds between 1 and 9. And then turn on the next page and you got any of the either 11 or 13. Okay? Does that make sense? The last section that we're coming to in chapter 5 is 5.6. That's the law of action and reaction. Remember, Newton had three laws. The law of inertia that he and Galileo worked on, not together. Galileo died before he was born. But that is Newton's first law of inertia, actually developed by Galileo but refined by Newton. The second one was the one we had a little earlier. Force is equal to mass times acceleration. The third law is the action-reaction force, is the law of action and reaction. If you've all got a book, and I didn't find out that, I want to say Devin, do you have a book yet? Devin? I see his iPhone still here, but I don't know if he can hear me.
Yes, sir. I can hear you.
Okay, do you have a book?
No, sir. I don't have a book yet.
Okay, but are you getting one soon?
Yes, sir.
Okay.
Yes,
Well, I will write down for you because the rest of them had books. So I'm going to clear the screen for you, and I'll type in, and this is a little bit easier to read than my writing. Here is Newton's third law, the law of action and reaction. Newton's third law. And here's how it goes. For every force applied by an object or by object A to object B, okay, that's the action. A acting on B, that's the action, okay? There is an equal but opposite force exerted by object B to object A. What? Okay, they said to also. Okay. I don't know why they don't say on, but they say to object A. Okay. Now to make that a little easier to read, maybe I'm going to stretch this out some. Okay, it's more like it is in the book. For every force applied to an object by another object, there is an equal but opposite force exerted on the other object by the first object. And that is, by the way, the reaction force. The force of object on A on B, that's your active force. The one from B to A is the reactive force. Here is how I understood Newton to describe it. Okay, I wish I had something I could do here. Okay, here is my book. Okay, I'm going to push with my finger against my book, and I'm holding with this hand pushing against it. The finger is pushing on the book, and if you look at my finger, you'll see it indented it, right? That means the book was pushing against my finger, okay? That's an example of action-reaction. The action was my finger on the book. The reaction was the book on my finger. And the way Newton said it, or I understand that he did, I wasn't around then, he said, if I push on a rock with some force, the rock pushes back on me with the same but opposite force. Equal but opposite. Okay? Now, how does this compare to the first two forces, Newton's laws? The first law was the law of inertia. If an object is at rest or in motion in a straight line motion in one direction, horizontal motion in one direction, it maintains that state of motion unless it's acted on by an outside force that changes the motion. That's the law of inertia. The law of inertia is the characteristic of an object that resists the change of motion. So that's the law of motion, of inertia. First law, an object maintains its inertia unless it's acted on, maintains its motion unless it's acted on by an outside force. Now notice there you just have one object. You may have outside forces, but you just have the one object. Okay, his second law. If there is an outside force acting on that object is going to change its motion. Changing its motion means accelerating. That means if it's going this way, it'll speed up, or it will slow down because it's being opposed by a force. Or if it's going this way and the force is this way, it changes the motion. Okay? Changes the motion, change of velocity, changes the vector direction that it's going. Any one of those is a change of velocity, that's an acceleration. And that's where we got the thing. The net force acting on an object is its mass times its acceleration. If there's no acceleration, there's no net force. Okay? If there is an acceleration, there has to be a net force somewhere acting on the object. But again, you have one object. The third law, though, you have two objects. One hit this way, the book this way, going, pushing on each other. And if this is pushing this way, this is pushing that way with the same force, just the opposite direction. That is the action-reaction force. Okay? Now, one example of that, let's go back to our slides. Well, two examples. So let's go back to, where is my slide? Okay. I hope this isn't going to end it for good. No. Okay. Let's go back to the slide set. And here it is. All right. That was the one on friction. This is so aggravating. I have to click on the slide before it will advance. Okay. And let's go to current slide. All right. No, it went back to the other one. All right. Here we have a car moving down the road. You know there's friction between the tire and the road. I can't get my cursor. There it is. There's always friction between the tire and the road. But the car is being pushed ahead by the engine here, pushing, if this is a front wheel drive, it's pushing against the road here. So you have 100 pounds of friction from the road, but also from the air resistance, okay? A total of 100 pounds of force resisting the motion, 500 pounds of force pushing you ahead. That is a net force of 400 pounds that the tire is pushing on the road. But, if the tire is pushing on the road with 400 pounds of force, the road is pushing on the tire with 400 pounds of force. That's Newton's third law. The net force is adding this force up in this direction, that force in that direction, a net force of 400 pounds, like we were just doing. However, if the net force is 400 pounds, Newton's third law says the same force with which the tire is pushing on the road, that same force is what the road is pushing on the tire. That's not Newton's third law. The other was the second law of force. In fact, this picture is for one of the problems. I didn't realize that. This is I can't see which one it is. Okay. Now, here is they don't have the second one. The second figure that's in your book, but it's not on the slide set, that shows the force of the ground on the tires is one direction. If they had done this, the force of ground on tires would be in this direction. The force on tire on the grounds would be on this direction. They would have to be equal and opposite because those are third law forces. How can you tell it's different? Because they're acting on different objects. Tire on ground, ground on tire, two different objects. This was net force because it's engine pushing the car forward, friction pushing the car backwards. Both of them are acting on the car. Okay, that is net force. The third law would be tire on road versus road on tire. Those are equal and opposite, always in opposite direction. Now here's another example of the third law. Okay, I don't like this example because I don't particularly like guns, okay? I was a gunnery officer in the Navy, so I have had to fire them. I've had to be in charge of them. I still don't like them, okay? Now, when you pull the trigger on the gun, okay, this is a pistol. When you pull the trigger on it, the hammer here hits the back of the bullet. The bullet has dynamite in it, actually something like dynamite, that it responds to that sudden compression and heats up very fast and sets it on fire. And that fires the bullet out the end. Well, the action on the bullet is a force in this direction. That is the bullet, the gun on the bullet. This is the this is really the way they've labeled it is not very good. Okay, the force of the gun on the bullet is in this direction. The force of the bullet on the gun is in that direction. I wish they hadn't said this on the hand, because the hand's not pushing on the bullet. The gun is pushing the bullet forward, and the bullet is pushing the gun backward. And that's why you always have recoil, okay? If you've ever fired a pistol, you know that it always tends to push your hand up. So a lot of times when you see on the Cops and Robbers show, they're holding their hand in place so they keep it level, okay? That's to keep the hand from flying up, because it always happens. The same force that the gun is exerting on the bullet is exerting on the gun, but in the opposite direction. So I wish they had said this differently. Action of gun on bullet, bullet on gun. Okay? Now, of course, the gun does it on the hand. Okay. Looks like somebody either else is coming in or someone had to go out. Oh, wait, we're still at 6, so evidently someone had to leave and come back.
Tell her the appeal is on the job, and not how you go on the court. Yeah, the job had to quit. That she the job, I know she got her appeal lately. It's the job, and she volunteered to quit.
Okay, was that talk to me or somebody else?
It went through.
Were you talking to me or somebody else? Okay, was the microphone on by mistake, or was that intended for me? I couldn't make out what you were saying. Okay.
I'm sorry, I lost service, so I had to reload.
Oh, you lost service. Got it. Okay, and who's talking?
Mika.
Mika. Okay, welcome back, Mika. Okay, I couldn't tell because you can't see this, but there is a window that comes up, and anytime someone enters or leaves, that blocks it out and says, move this window away from the shared application. Well, I can't move it. It doesn't let me move it. So when you come in or leave, or no, when you come in, it blocks who's the name. So that's why I couldn't tell. All right. That's Newton's third law. There aren't any problems with it, but there are a couple of things that are listed. Let me see if they're on the slide set. I don't think so. Well, I can't get the slide set to move until I click on it again. Okay, still 6 people in the class. Okay. Yep, that's the last slide on the show. Okay, but in your book, you'll see a couple of others. I'm just going to hold it up. Here is an example. It's called the balloon rocket. What you do is have something like a zip line. You could use a clothesline or anything else like that, with a tube in it. Tape somehow a balloon to the tube, and then blow up the balloon, release the nozzle, and you got the thing shooting down the zip line. Okay? That is Newton's third law. The air moving out of the end of the thing pushes the balloon forward. The force of the air on the balloon on the air this way, equal and opposite the air on the balloon that way. Newton's third law. That's exactly how rockets work. Okay? Okay? That's the space shuttle. That's the old picture because they don't have the space shuttle anymore. But the exhaust pushing downward from the booster, that's the action force. The exhaust pushing upward on the booster, that's the reaction force. The booster pushing down with the exhaust is the active force, and the reactive force is the exhaust pushing the booster up. That's why rockets work. Okay. Action, reaction. In fact, you could do a little study. One of the first flying devices was a blimp, a Zeppelin they called it. And that was exhausting something. Think of a balloon. Exhausting air in that direction pushes the balloon in that direction, just like the picture at the bottom of the page. They call it a balloon rocket. Well, after that, they had a prop plane. Well, how did a prop plane work? A propeller-driven plane. The propeller goes like this, pushing air backwards, pushing the air backwards. The plane is doing that. The air pushes the plane forward. Action, reaction. Then we had jet airplanes. We still do. Okay? Here, the exhaust is pushing this way. The plane is pushing the exhaust this way. The exhaust is pushing the plane that way. Action, reaction. Then you have rocketry. The exhaust is pushing the rocket is pushing exhaust downward. Exhaust pushes the rocket upward. Action, reaction, all the way. And by the way, here was the formula. Whatever the action force is, the reaction force is equal to it, but opposite in direction. So that's why you have the minus sign there. And that does finish the end of chapter 5. There is a glossary at the end, which goes over a lot of the key terms. I'll show you just the first part of it here. Okay. It goes on to the next page, just a little bit at the top of the page. When you get your book, you'll see that. Then there's formulas there, not too many of them, but a few. Review questions, those are usually multiple choice or something like that. But then comes the problems. The problems are the best things to review. They're called review problems. And again, I think the odd numbers have answers in the back, so you could do any of those odd number review problems 1 to 17. You don't need to, okay? But you can if you want to, if it helps you understand them better, because the answer's in the back. And what I say you don't need to, if you listen to when I talk about the syllabus, the dean wants us to have some sort of input, I think, from either every class or every week. I don't know which he wants, but here's what yours will be for this time. You don't have to send me a problem that you've worked on from the odd number exercises, because after class is over with, I'm sending you the first test, the chapter 5 test. It'll be in Word format. I'll send it to you on Blackboard Messages. Remember, that's the thing that looks like the envelope. Okay? That's where you'll find it. It'll be sometime after class is over, because I'm recording still. Let's see. How are we doing on time? Oh my goodness, what gracious. We've just gone over. But guess what? Here's the good news. And there's no extra charge. But before we get that done, let me point out to you the next chapter we cover is chapter 8. That's work and energy. So we'll be moving to chapter 8 next time. I'll be sending you, after class today, your test for chapter 5. It's also called test 1. Any questions? Let me say this about the test. You have a week to work on it. More if you need it, but at least a week. That allows you to ask me questions on Thursday. If something you don't understand, don't know what it's looking for, I'll try to explain things on Thursday. Then try to get me your test sometime Tuesday or as soon after Tuesday as you can. What I want you to have that test back before I give you the test on chapter 8. Chapter 8 is not a particularly long chapter, so please, we finish chapter 5 in 4 sessions, Tuesday, Thursday, and Tuesday. So we'll probably finish chapter 8 in about 4 sections. So please get me the chapter 5 test 1, as soon as you can. Okay? but try to get it to me within a week or two. Okay? Any questions? All right. If no questions, I'll stop the share. And now you can always ask me questions on homework exercises. Even though you're not turning them in, you can still do them and ask me if you have any questions. So I'm going to stop the share, and then I'm going to end the meeting. Any final questions before I end? No. Okay. Take care. Be safe. I'll see you on Thursday evening. Okay? All right.
Yep.
Bye-bye. 6:15. Oh. Okay. Oh, yuck, 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 yuck.